let's look at this problem involving a submarine down under the ocean. So it says, while exploring a sunken ocean liner, the principal researcher found the absolute pressure on the robot observation submarine at the level of the ship to be 413 atmospheres. The density of seawater is 1,025 kilograms per cubic meter. Calculate the gauge pressure, PG, on the sunken ocean liner. So if absolute pressure is the gauge pressure plus atmospheric pressure, then gauge pressure must be equal to the absolute pressure minus atmospheric pressure. So they're saying right here that the absolute pressure was 413 atmospheres. So the gauge pressure then is the absolute 413 minus 1 atmosphere, which is atmospheric pressure. So the gauge pressure is 412 atmospheres. You can leave it as that for this problem, or for the other problems we'll have to convert it. So I'm going to go ahead and do that. 413 atmospheres, if we multiply that by 100,000 pascals, because each atmosphere is 100,000 pascals, we clearly will get there in this case. Whoops, sorry, it's not 413, it's 412 is our answer from here. So if you multiply that out, you get 41,200,000 pascals is the pressure there. B says calculate the depth D of the sunken ocean liner. So since we already know this gauge pressure, this is what's being caused by the fluid there. So we can just focus on that. The gauge pressure will be density times gravity times height. So the pressure caused by the fluid there. So we can set this up and solve for it. We already know that the gauge pressure is 41,200,000. Density of the seawater is 1,025 kilograms per cubic meter. The G is 10 meters per second squared, and so we will solve for the H there. And when you go to solve for this, you get roughly 4,020 meters must be the height. So that is the depth down in the ocean. So next question says, calculate the magnitude of the force due to the water. So this is important, not overall the air and the water, but just due to the water on a viewing port of a submarine at this depth if the viewing port has a surface area of 0.01 square meters there. So to find this force, we know that pressure is the force per area. So force is equal to pressure times area. The force then in question, the pressure due to the water, is 41,200,000 pascals. And the area, they straight up gave it to us, is 0.01 square meters there. So just multiply those two, and the force you will get is 412,000 newtons. All right, the last two are actually kinematic problems. So it says, suppose the ocean liner came to a rest at the surface of the ocean before it started to sink. Due to the resistance of the seawater, the sinking ocean liner then reached terminal velocity of 10 meters per second after falling for 30 seconds. Determine the magnitude of the average acceleration of the ocean liner during this period of time. So this one is simply that the acceleration is the change in velocity over time. We know the change in velocity is 10 meters per second because we started at rest and got up to that speed. The time is 30 seconds, and so the acceleration is 0.33 meters per second squared. Then they say, assuming the acceleration was constant, calculate the distance d below the surface at which the ocean liner reached this terminal velocity. So when did we get to our final speed? Well, we already know, and we're looking for a distance, so a good equation to use would be what we call the third one. The position is the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared. Let's just call our initial position 0. We know our initial velocity is 0, So those are gone. And so now we're down to our position is 1/2 times our acceleration times time squared. Now we can simply plug in for these. So our acceleration we solve for up here, 0.33 meters per second squared. Our time is 30 seconds. Don't forget to square that. And our position that we'll get there is about 150 meters. So after that point, the ship is at terminal velocity.